Security by design, not by addition. Opening the wall around the swimming pool. There's a moment that every security architect has experienced, even if they have never named it as such. A product team reaches out, not at the beginning of a project, but somewhere close to the end. The launch date is weeks away. The code is written, the database schema is finalized, the API contracts are set. And now, with all of that locked in place, the question arrives. Can you take a look at this and make sure it is secure? What follows is one of the most frustrating exercises in applied security. The architect reviews the system and finds problems. Not surface problems, not a missing header or an overly permissive CORS policy, but structural problems. An authentication model that assumes trust between services that should not trust each other. A data model that stores sensitive information in a place that makes encryption prohibitively complex without rewriting significant portions of the application. An API design that exposes object references in a way that allows any authenticated user to read any other user's data by changing a single URL parameter. Each of these problems has a correct solution. The correct solution requires changes to the design. The design is already built. The cost of the correct solution, measured in time and rework and delay, is now an order of magnitude higher than it would have been if the question had been asked 3 months earlier. This is what the principle of security by design, not by addition, is pointing at. Not as a critique of engineering teams who did not know better. Not as a governance failure that could be fixed with a stricter review gate, but as a fundamental reality about the economics of when security knowledge enters the development process and what it costs depending on where it enters. Security decisions made at the design phase cost almost nothing to implement. The same decisions made after the system is built cost dramatically more and produce worse outcomes. The architecture is already committed. You're no longer choosing a design. You're choosing a workaround. This session works through what it actually means to build security into the foundation of a system rather than attach it to the outside of one. Not as an abstract principle, but as an implementable practice, with the tools that enforce it, the failure modes that reveal when it was skipped, and the organizational dynamics that make it sustainable or undermine it before it can take root. The foundation, what secure design actually means. The vocabulary here needs to be precise, because several terms are commonly conflated in ways that produce genuine confusion about what is being asked for and who is responsible for it. Secure coding refers to the discipline of writing software in a way that does not create exploitable conditions. Buffer overflows occur when a program writes data beyond the boundary of an allocated memory region, allowing an attacker to overwrite adjacent memory and potentially control program execution. SQL injection occurs when user-supplied input is incorporated into a database query without sanitization, allowing an attacker to modify the query's logic and access data the application was never intended to expose. Cross-site scripting occurs when untrusted data is included in a web page without encoding, allowing an attacker to inject script that executes in the browsers of other users. These 3 vulnerability classes have been on every security practitioner's known and preventable list for more than 20 years. They still appear in production systems, not because developers are unaware of them, but because secure coding must be systematically built into how code is written, reviewed, and tested. Knowing about a class of vulnerability and having the tooling, process, and culture to prevent it consistently are different things. A threat model is a structured analysis of what could go wrong in a system before that system is built. The STRIDE methodology organizes threat analysis into 6 categories: spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. A STRIDE session applied to an architecture diagram asks each of these questions systematically for every component and every data flow. The outputs are specific, named threats that can be evaluated for likelihood and impact, and then addressed through design decisions before construction begins. A threat model is not a risk assessment. A risk assessment evaluates the likelihood and impact of potential events at an organizational level, considers existing controls, and produces a risk treatment decision. A threat model operates at the system design level, produces a structured list of specific attack scenarios against a specific architecture, and feed design requirements rather than risk management decisions. Both are necessary. They operate at different layers and answer different questions. An information security management system is the organizational framework within which security policies, standards, and practices are defined, implemented, reviewed, and continuously improved. ISO 27001 is the most widely adopted framework for building an ISMS. It specifies what the organization must be able to demonstrate: that it has identified its information assets, assessed the risks to those assets, selected and implemented controls to address those risks, and is reviewing whether those controls remain effective. The ISMS is the organizational context within which security by design operates. Without it, secure development practices may be applied in one project team and absent from the next. With it, the expectation of secure design becomes an organizational commitment with defined accountability rather than a project-by-project negotiation. The relationship between these 3 layers is worth making explicit. The ISMS provides the governance that makes secure development a requirement rather than a suggestion. Threat modeling provides a design phase methodology that makes security requirements concrete and architecture-specific. Secure coding provides the implementation-level discipline that ensures those requirements are realized in the software that gets built. A gap at any layer produces a different failure mode. An ISMS without threat modeling produces an organization with security policies, but no mechanism for translating them into technical design decisions. Threat modeling without secure coding produces architectures designed to be secure, but implemented without the practices that prevent code-level vulnerabilities. Secure coding without an ISMS produces careful developers in organizations where no governance structure requires or rewards their care. The structural tension, speed, completeness, and the cost of later. The tension at the heart of security by design is not between security and development. It is between the cost of knowing something now and the cost of acting on that knowledge later. Consider the banking mobile application scenario. The project manager's argument for skipping threat modeling is not irrational. A STRIDE session consumes time. Developers and architects who participate in it are not writing code during that session. The project is on a 3-month timeline. Every day spent in design review is a day not spent in development. From the project manager's vantage point, the security review is a cost that delays a launch and produces documentation, not a functional capability visible in the delivered product. This framing is correct in its accounting of costs and incorrect in its accounting of risks. The STRIDE session takes 1 day. The ID or vulnerability it reveals, where one user can read another user's account balance by changing a URL parameter, takes 1 day to fix at the design stage. Change the data model to use non-sequential identifiers and enforce authorization at the query level rather than at the URL parameter level. A schema change and a query change. It is unglamorous, and it takes a day. The same vulnerability discovered after the application launches takes dramatically longer to address. The schema change requires a migration of existing data. The query change propagates through multiple services built assuming the current model. A WEF rule can be deployed as a compensating control, but a WEF rule attempting to detect IDOR by pattern matching on parameter values will produce both false positives and bypasses, because IDOR is a business logic flaw, not a recognizable attack signature. The fix is not a WEF rule. The fix is what it was at design time: a schema change and a query change, now touching a production system with live data and dependent components. The same work costs 10 times as much. The second dimension of the tension is organizational. Developers who experience the security team primarily as a review gate near launch, the people who show up with a list of things that need fixing before the launch can proceed, experience security as an adversarial function. The security team appears when things need to change, and the changes it requires cost time the development team does not have. This adversarial dynamic produces a predictable pattern. Teams minimize security involvement, bring security in as late as possible, and then resist findings because the cost of remediation is genuinely prohibitive. Security by design does not just change when security is applied. It changes who applies it. When security considerations are embedded in the design process from the beginning, they become decisions the development team makes rather than requirements imposed afterward. A developer who participates in a threat modeling session and identifies a risk in their own proposed architecture is not a developer who resists the finding. They are a developer who understands a risk and knows why the design choice they made creates it. That understanding is what produces design changes that hold. Changes made by someone who grasps the problem, rather than changes made to satisfy a reviewer. Architecture: the 4 phases where design decisions are made. Security by design is not a single activity. It is a set of practices applied at 4 distinct phases of the development lifecycle, each corresponding to a different kind of security decision and a different cost of getting it wrong. The design phase has the highest leverage. Before a single line of code is written, the architecture determines which security properties are achievable and which require fundamental rework. The shape of the data model determines whether encryption at rest can be applied granularly. The authentication model determines whether MFA can be added without re-architecting session management. The choice between synchronous and asynchronous service communication determines the lateral movement surface available to an attacker who compromises one service. Threat modeling at this phase, a stride session applied to the architecture diagram, surfaces these decisions while they are still decisions rather than constraints. The development phase is where secure coding practices and static analysis tooling operate. A SaaS tool integrated into the CI pipeline provides immediate feedback when code patterns associated with known vulnerability classes are introduced. It does not wait for a separate security review to identify that a parameterized query was written as string concatenation, or that user input is being written to the DOM without encoding, or that a cryptographic key is hard-coded in configuration. The limitation of SAST is that it operates on code in isolation and cannot evaluate the business logic of the application or the correctness of the authorization model. It finds implementation errors in known vulnerability classes. It does not find design errors. The deployment phase is where infrastructure as code tooling operates. IAC, defining infrastructure configuration in version-controlled code rather than through manual provisioning. Make security guardrails enforced by default rather than verified by review. A policy that prohibits S3 buckets from having public read access does not require a security team to audit every deployment. The policy evaluation runs automatically in the pipeline, and a deployment that would create a publicly accessible bucket fails before it reaches production. Policies enforced in the pipeline are violated or not at the moment of deployment, with no gap between the standard and its enforcement. The testing phase is where vulnerability scanning and dynamic application security testing operate. By this phase, many design and implementation decisions are locked. Testing phase tools serve a validation function, confirming that earlier phase practices produce the expected security properties, rather than a design function. A penetration test that discovers an IDOR vulnerability here is not providing new information about how to build the system securely. It is providing evidence that the design phase threat model did not catch a specific class of authorization flaw. That evidence should feed back to the design phase. Not just fix this instance, but update the threat model template to include IDOR as a systematic check for any API that exposes object references. Tools that enforce security at the point of decision. 4 tools deserve attention, not for what they do in the abstract, but for which specific security decision each one makes concrete, what it costs organizationally, and where it fails to deliver what security teams sometimes expect. Threat modeling with Stride is the tool that enforces security at the design phase, and its primary benefit is not the threat list it produces. It is the conversation it creates. A Stride session that brings together the architect, the developers who will build the system, and a security engineer is a session where security knowledge flows in both directions. The security engineer learns what the system is actually trying to do, its data flows, its trust relationships, its external dependencies. The development team learns what an attacker would find interesting about the system they're building. The failure mode specific to this tool is the threat model produced by the security team alone, without the development team, delivered as a document that developers receive and do not read. A threat model produced without the people who design the architecture will miss the implementation details that turn theoretical risks into actual vulnerabilities, because the security engineer is reasoning from the diagram, and the diagram is an abstraction that omits the decisions made to simplify it. SCSD tools are the enforcement point for secure coding at the development phase. The organizational cost is tuning. An untuned SCSD tool applied to a large code base generates finding volume that exceeds analyst capacity, and finding volume that exceeds capacity produces a queue that developers learn to dismiss. A SaaS program that produces 1,000 findings on day one without a prioritization and remediation plan produces SCSD fatigue faster than security improvements. The limitation is scope. SCSD finds implementation errors in the code it analyzes. It does not find authorization logic errors that require understanding business context. It does not find misconfigurations in infrastructure. It does not find vulnerabilities introduced by third-party libraries. That is the domain of software composition analysis. SCSD is one instrument in the tool set, not the tool set. IAC security scanning tools, policy as code frameworks that evaluate IAC configurations against security baselines before deployment, enforce the security properties of infrastructure at the deployment phase. The benefit is eliminating configuration drift vulnerabilities. The security group rule added manually to solve a specific problem and never reviewed again. The storage bucket made public to test something and never returned to private. When infrastructure is defined as code and evaluated against policy before deployment, every change is a reviewable artifact. The organizational cost is calibrating the policy library. Policies too strict block legitimate deployments and create pressure to bypass them. Policies too permissive miss the conditions they were designed to catch. Software composition analysis tools address the supply chain dimension. Modern applications are not primarily written code. They are primarily assembled dependencies, and the application security properties depend heavily on every library it incorporates. An application with no vulnerable code of its own, but a critical deserialization vulnerability in a dependency, is a vulnerable application. SCA scans the dependency manifest, produces a bill of materials, and cross-references every component version against known vulnerability databases. The limitation is the difference between a vulnerability being present in a dependency and being reachable and exploitable in the application. SCA produces presence findings. Risk assessment requires understanding the application's actual use of the affected component. Implementation, building the secure SDLC into the pipeline. Two implementation scenarios span the spectrum from organizational governance to technical enforcement. The first is implementing SDLC practices in a CI/CD pipeline that currently has none. The starting point is not the tooling. It is a gap analysis. Review the repository configuration for branch protection rules, the CI pipeline for what validation steps exist, the container registry for whether unsigned or unscanned images can be deployed, and the deployment configuration for whether infrastructure changes are gated on policy evaluation. From the gap analysis, the implementation plan builds sequentially rather than applying all controls simultaneously. The first change addresses the highest impact gap with the lowest disruption to developer workflow. In most cases, this is a CSD integration into the PR review process, configured in audit mode initially. Findings are surfaced but do not block merges, while the development team works through the existing finding backlog and tunes the tool to suppress false positives in accepted risk categories. Once the finding volume is manageable, critical and high-severity categories are promoted to blocking status. The developer who introduces a critical vulnerability now sees that finding before their PR can merge in the context of the code they wrote, with a description of the vulnerability class and a suggested remediation. SCA integration follows the same pattern. Audit mode first, then blocking on critical severity findings with known exploits in the wild. IAC policy evaluation follows, starting with the highest confidence rules before expanding to more nuanced policies as the team develops familiarity with the tool. The implementation requires more than tooling configuration. It requires communication to the development team about what each tool does, why each check is being added, and what the process is for disputing a finding believed to be a false positive or an accepted risk. Development teams that receive new pipeline gates without explanation experience them as imposed obstacles. Development teams that receive a briefing explaining that these checks target the vulnerability categories most frequently observed in the current threat environment, and that there is a clear escalation path for cases where the check is wrong, experience them as professional support for writing secure code. The second scenario is a three-tier web application architecture designed with security controls at each tier from the outset. The web tier, load balancer, and reverse proxy handling inbound traffic, terminates TLS, enforces transport security policy, and delivers only validated requests to the application tier. The application tier is designed with an explicit authorization model. What roles exist, what resources each role can access, and how the authorization check is enforced in code rather than delegated to the client. The database tier is designed with field-level encryption for sensitive data, connection access restricted to the application tier service account, and query parameterization enforced at the data access layer. Each of these design decisions costs approximately 0 at design time and scales with system complexity at remediation time. The TLS termination point is a one-line infrastructure decision at design time and a load balancer reconfiguration requiring downstream service updates after deployment. The authorization model is a design session and a set of code patterns implemented consistently from the start, and a full endpoint audit plus access control rewrite after deployment. The database encryption is a schema decision at design time and a migration project plus query rewrite plus application update after deployment. The entire architecture review takes a few days. Remediating the same vulnerabilities in production takes months. When security by addition fails, 3 diagnostic scenarios. 3 failure scenarios illustrate the specific mechanisms by which bolt-on security fails in ways that design time security does not. The first scenario is the container image vulnerability deployed to production despite image scanning being configured in the CI/CD pipeline. The pipeline logs show the scanner ran on every build. The question is why the scan did not prevent the deployment. The diagnostic begins with the scanner's failure threshold configuration. Image scanners can be configured to fail the build on findings above a severity threshold or to report without blocking. If the scanner is in report-only mode, the finding was visible but did not prevent deployment. Pull the scan results for the build in question and check the threshold configuration. If the threshold was set to block on critical findings, the second diagnostic question is the base image tag. If the build uses a pin tag rather than a digest, a previously scanned and approved version may have had its vulnerability database updated after the scan was cached, and the scanner may have returned cached results rather than rescanning the current state. The correct configuration is scan by digest, not by tag, with no result caching between builds. The third diagnostic question is timing. If the CV was published after the image was built and scanned, the scanner would not have detected it. It was not yet in the vulnerability database at scan time. This is not a configuration failure. It is the inherent limitation of point-in-time scanning in a continuous deployment environment. The operational response is continuous vulnerability monitoring of deployed images, not just pre-deployment scanning. The guardrail that prevents this category of failure by design is an admission controller in the cluster, a policy enforcement point that validates every container image against a signature registry before it is permitted to run. Images not signed by the CI/CD pipeline's signing key cannot be admitted, regardless of how they were pushed to the registry. The second scenario is the WAF not blocking SQL injection attacks, with logs showing attacks reaching the application unimpeded. The diagnostic question is whether this is a WAF configuration failure or an application design failure, because the answer determines whether the correct response is a WAF rule or an application code change. Pull one of the attack requests from the application logs and examine it. If the request contains a recognizable SQL injection payload and the WAF did not flag it, the WAF either lacks an active rule set or is in detection-only mode. Check the policy configuration. If the WAF has an active blocking rule set and the attack still reached the application, the next question is whether the payload was encoded in a way that evaded pattern matching. URL encoding, double encoding, Unicode normalization. The short-term fix is encoding normalization in the WAF's pre-processing pipeline. The correct long-term fix is parameterized queries in the application's data access layer. A WAF rule attempts to recognize attack patterns. Parameterized queries remove the mechanism that SQL injection exploits. These are not equivalent controls. The WAF is a compensating control for a design failure in the application. The design-level fix is the application change. The WAF rule is a band-aid on a structural problem. The third scenario is a container image scanning step that is not catching vulnerabilities because it is evaluating the wrong artifact. In a multi-stage Docker build, a team configures the scanner to run against the final production image, while the vulnerable component is a build time tool that did not make it into the final images package list. But the compiled binary it produced, included in the final image, links the vulnerable library statically. The scanner evaluates installed packages in the final image and finds nothing because the vulnerable component is not in the package list. This gap cannot be addressed by configuring the scanner differently. The scanner is doing what it was designed to do. The correct response is SBOM generation at the build stage, capturing the full bill of materials, including build time dependencies and statically linked libraries, and scanning the SBOM rather than the final images package list alone. This is a pipeline design change, not a scanner configuration change. The lesson it illustrates is that the specific mechanism by which a tool enforces security matters as much as the presence of the tool. 3 roles, 3 points of intervention. The same principle looks entirely different from the perspective of a security architect responsible for the design of a system, a detection engineer responsible for finding threats in a running environment, and a security automation engineer responsible for the pipeline that builds and deploys that environment. The security architect's defining moment in the context of this principle is the threat modeling session, where an architectural decision is being made that the development team has not fully evaluated for its security implications. The architect's value in that session is not the authority to require a particular design choice. It is the ability to articulate what a specific architectural decision means for the system's attack surface, not in abstract security terms, but in the specific operational terms that make the implication concrete for the people in the room. When the architect says that the proposed microservice communication model, where Service A trusts any request claiming to come from Service B, creates a lateral movement path that would allow an attacker who compromises Service C to impersonate Service B and extract Service A's data, and then draws that path on the architecture diagram. The room understands why mutual authentication between services is worth the implementation complexity. The architect who makes threat scenarios specific and visual is more effective than the one who recites the correct requirements, because understanding changes design decisions while compliance changes documentation. The detection engineer's relationship with security by design runs in a specific direction. They see, in the alert queue, the consequences of design decisions made without security consideration. A detection rule for SQL injection payloads in HTTP request logs exists because the application was designed without parameterized queries. A detection rule for unauthorized lateral API calls between microservices exists because the inter-service authentication model was not designed to enforce caller identity. The detection engineer's contribution to the design conversation is empirical evidence of what attacks are actually being attempted against systems like the one being built, drawn from real attack data in threat intelligence feeds and incident history, and the translation of that evidence into concrete design requirements. When a detection engineer tells the architecture team that the majority of API attacks in the current environment target broken object-level authorization and that every resource endpoint should therefore enforce ownership verification at the query level, they are converting detection data into design requirements. That is the most direct contribution detection capability can make to design security. The security automation engineer encounters security by design at the pipeline level, and their defining challenge is making security gates invisible in the good case and clear in the bad case. A pipeline gate that fails silently, or that fails with a cryptic error message requiring developer investigation to interpret, creates friction that produces pressure to bypass the gate. A pipeline gate that fails with a message naming the specific finding, the specific code location or configuration, the specific policy violated, and the specific remediation path, and that takes less time to address than to escalate, produces developers who fix the finding. The automation engineer who builds that experience into the pipeline is doing security by design at the developer experience level, making the secure behavior the path of least resistance through the quality of the tooling interface rather than through the severity of the enforcement policy. Case scenario: the banking app and the 3-month window. You are the security architect at a regional bank. The product team has been developing a mobile banking application. The application allows retail customers to view balances, transfer funds between accounts, and make bill payments. 3 weeks into the project, the engineering lead reached out for a design review. You conducted the review and identified a concern in the API design. Account resources were addressed by sequential integer IDs, and the API's authorization check validated that the authenticated user had an account, but did not validate that the account being requested belonged to that user. Any authenticated customer could retrieve any other customer's balance by changing the account ID parameter. The engineering lead's initial response was that the API security gateway, recently deployed, routing all mobile API traffic, could be configured with rate limiting to prevent automated enumeration. You held the conversation that the WAF could not resolve. Enumeration is a detection problem, not a prevention problem, for a vulnerability that requires a single request to exploit. A customer who knows their own account ID and a neighbor's needs one correctly formatted API call. The gateway has no rule that prevents this because there is no attack signature. The request is a perfectly valid API call, correctly authenticated, correctly formatted, requesting a resource the server will return because the authorization model does not check ownership. The constraint was real. The project timeline was committed to the retail division, which had integrated the launch date into its marketing calendar. The engineering team had 18 working days before user acceptance testing. The mobile client was developed by a third-party vendor whose sprint cycle meant schema-driven changes required 2 weeks of lead time. You restructured the remediation plan around what could be implemented within the existing constraint rather than advocating for a timeline extension that was not going to be granted. The database change, migrating account IDs from sequential integers to UUIDs, Was a migration scriptable and runnable in a maintenance window with a 2-hour rollback capability? The API layer change, adding an ownership check to every account resource endpoint, was a 2-day development task within Sprint. The mobile client change was the constraint, 12 days for the third-party vendor, running in parallel with the UAT period. The API gateway was configured to reject requests using the old integer ID format after the migration window, not as the primary security control, but as a transition boundary that would surface an explicit error for any client that had not updated rather than silently returning data. You documented the design change in the project's architecture decision record with a section on why the WAF's compensated control approach was rejected. The rationale was economic and technical simultaneously. A WAF rule monitoring for sequential parameter enumeration would require continuous tuning as the account base grew, would produce false positives that blocked legitimate customer transactions, and would fail entirely against a single request exploit from a customer who knew the target account ID through non-automated means. The ownership check in the API layer, implemented once and enforced on every request, had none of those properties. Its implementation cost was 2 development days at the point of design change and 0 ongoing operational cost. The WAF rules implementation cost was lower, but its operational cost was indefinite and its security guarantee was weaker. The post-launch penetration test found no IDOR vulnerabilities. It did find 2 other issues: a rate-limiting configuration too permissive on the fund transfer endpoint, and a session token that did not expire on explicit logout. Both architectural decisions the initial Stride session had not surfaced because the session had focused on data confidentiality and authentication threats rather than session management and transaction integrity. You documented both findings in the threat model and used them in the retrospective with the engineering team as examples of what a single session Stride review does not catch, and as the argument for iterative threat modeling at each significant design decision rather than a single session at project initiation. Closing. The architect who arrives before the blueprint. The principle this session has been building toward is not a technical prescription. It is a way of understanding when security decisions have the most leverage, and then consistently choosing to make them at that moment rather than the most expensive one. A firewall deployed in front of a system built without an authorization model is not defending the system. It is performing security theater at the perimeter while the system's fundamental design remains as vulnerable as it was before the firewall arrived. The firewall cannot fix the authorization model. It can only make some attacks harder to execute automatically, and only the ones that look like attacks to its rule set. The architect who arrives before the blueprint is drawn is the one who changes what gets built, not what gets bolted onto the side of what was already built. That architect does not have the authority to slow down every project or make every decision, but they have the timing to make the decisions that matter most cost almost nothing instead of costing enormously. The posture this principle is building is one of systematic earliness, the habit of asking the security question at the design review instead of the launch review, of running the threat model when the architecture diagram is still a whiteboard sketch rather than a deployed production system, of building the secure default into the IAC template instead of auditing it out of the running environment. None of these require heroics. They require the same discipline that good engineering requires in every other dimension. The discipline of doing the harder thinking up front so that the implementation is the straightforward part. Security that was designed and does not need to be bolted on afterward. That is not just an engineering principle. It is a statement about where attention, time, and professional judgment actually produce durable results rather than perpetual remediation. End of session. Security by design, not by addition.